All right, I've got 2:15, so I'm going to go ahead and kick things off. Hi, everybody. Once again, my name is Sean Hewitt. I'm with SMRP staff, and I'll be assisting our speaker today as a Zoom host, monitoring the Q&A and helping out wherever I can. This session is entitled Digital Transformation Powered by the Industrial IoT and Predictive Analytics, and our speaker is Mo Abwali from IoTco LLC, pardon me, and we are in track 6. Before we begin, I have just a few housekeeping notes for you. Today's session is being recorded to be archived in SMRP's Body of Knowledge library, and the session will also be posted on the virtual conference website, which will stay live for 1 year, so until October of next year. If you have any questions for the presenter, please use either the raise hand feature, or probably the easiest thing to do is just ask your question in the chat function, which is located in the virtual conference platform, and you should see it just to the right of the window you're watching us in right now. If you have any technical questions, please use the Get Support option, and you can find this under the Account menu, which is located in the navigation bar at the top of every page on the far right. And yeah, just hit Get Support in the drop-down menu. At the end of the session, we ask that you please click on the Take Survey link, which you'll find located just below the session window, actually right underneath the session description. And once again, thank you to all of our virtual attendees for your continued support of SMRP. And now I'm going to put myself on mute and go ahead and hand it off to Mo.
Thank you, Sean. And thanks to the SMRP for the opportunity to give this presentation here. My name is Mo Abwali. I'm based out of Cincinnati, Ohio. I've been in the industry for about 22 years with experience around manufacturing specifically, mostly automotive manufacturing. And it's a pleasure to give you guys this presentation here today regarding digital transformation and what SMRP refers to as emerging technology. So let's start. Very briefly, who we are as a company, one simple slide. We are an organization that serves manufacturing. We come from manufacturing, we serve manufacturing, and we predominantly work with discrete manufacturers in aerospace automotive. You know, some of the logos here are companies that I've worked intimately with in the past 22 years. We have 2 domains of experience using analytics on the factory floor, but not just on the factory floor, also in smart connected products. Things like autonomous vehicles or assets out in the field that require monitoring and analytics. We also work in that domain. Although most of the applications we deal with today are within the connected factory applications within manufacturing. We serve industry with 3 practices. We're a team of over 50 people within our network. We have an analytics team referred to as PDX. We have an industrial data science team that comes from manufacturing, about 20 folks. We couple that with our academy. Our academy is our training and education, where we build relationships and create digital transformation and Industry 4.0 strategies for manufacturers. And the industrial IoT practice we have offers a turnkey solution around getting connected, you know, sensors, data acquisition, and also solutions that support manufacturing in terms of visibility and manufacturing execution and the Internet of Things. So, you know, our DNA is manufacturing, and it's really my pleasure to be here today to speak about 3 things. Okay, and I know I have a whole, you know, hour assigned to me by SMRP, which I do appreciate. I will not speak for an hour. I'll speak for, you know, 35 minutes or so. And if you have questions at any time, please drop them in the chat window. I will answer them, and I'd like to have at least 15 to 20 minutes at the end to answer your questions and concerns. But my vision for this presentation is, how can we drive towards a zero downtime, zero defect manufacturing vision? Okay, and I want to address this by covering 3 things. Number 1, setting the stage. Okay, what is predictive analytics, and how is it part of your Industry 4.0 strategy, or how it should be part of your Industry 4.0 strategy? what's the technology out there, and what are solution templates and mature, readily available type of approaches where you can actually start doing predictive analytics fairly quickly, okay? And I have ideas to summarize the presentation on what we call a systematic approach, where you can win ROI very quickly using industrial AI, okay? So let's start. I'd like to first set the stage. You know, even though this track is called Emerging Technologies, my presentation is not emerging at all, okay? The Internet of Things is a field that may have a new name, but has been around for decades, okay? IoT is by no means a new field. My wife works at GE Aviation. When a plane goes up to the sky, when it cruises, when it lands, there are snapshot data that are being sent somewhere. Before the machine lands from point A to point B, there is knowledge that a spare part is needed on the right engine of the plane, so you can fix the plane, so it can stay in a shorter period of time on the tarmac, and it goes up in the air, because you make money when the plane is up in the air, right? So IoT is about using data, communication, internet, connectivity, in the case of an airplane, and analytics, right? To provide a business case and decisions in a timely manner to your end user. You know, your end user, be it a factory or be it the customer or the fleet operator of an airplane, okay? But when we look at the industrial Internet of Things, we're looking at manufacturing, we're looking at industries. And if you look at industries today, you know, they are fragmented, I would say. You have machines on the factory floor, you have assets, right? You have, in some cases, SCADA systems, data acquisition systems is an easier word there. You have, in some cases, a manufacturing execution system or an IoT platform that is marrying data from the factory floor to the business layer, which is your enterprise resource planning layer, your SAP, your Infor, your Oracle, whatever you're using for your finance and HR and warehousing and all that good stuff, right? So Industry 4.0 as an initiative was formed to support industries to realize convergence between their IT, their information technologies, their ERP systems and other systems, and their OT, their operational technologies, the sensors, the devices, the machines on the factory floor, okay? And the initiative was originally born from Germany. A lot of us know that. And you know, in the US and other areas of the world, there are different namings sometimes for the initiative. Manufacturing 4.0 being the naming used by NAM, National Association of Manufacturers in the US. But you know, companies like GE and others have started to use their own brand names. You know, Brilliant Factory or Brilliant Manufacturing as an example from GE, okay? But if we look at Industry 4.0 and the analytics strategy, I want to simplify it in 4 pillars, okay? There are 4 pillars that needs to be part of an Industry 4.0 or an analytics strategy of any company. And I like to start from the right and go backwards. What is your business case? Okay. Business case drives technology adoption. No business case, no technology adoption. Okay. And you'll see this at the end of my presentation. I'm going to take you through a journey and we're going to talk about analytics and all kinds of fun stuff. But I'm going to come back at the end and say, it's about people, process, and technology, okay? And the business case needs to be very clear, and your people, process, technology strategy needs to be very clear to ensure the success of all these technologies and pilots on the actual factory floor, okay? So ROI is paramount here. Are you improving uptime? Are you reducing quality issues? Are you improving your spare part? What is your why? Okay. And if the why is clearly identified and justified, we start talking about, am I connected? Do I have the needed protocols on my machines to speak? Do I need sensors on my assets? Do I have a data lake? Where is my data going? Do I need data on the edge in my plant, or can I send data to a historian, right? These are all questions that need to be asked. And once the connectivity is in place and proper data is being collected, we talk about analytics. We talk about performance analytics sometimes, you know, what's my uptime, what's my OEE, how am I tracking my performance? But in this presentation, I'm going to focus about predictive analytics. What is the future behavior of my assets? Are my assets healthy to continue running with high uptime and to continue making good parts? Or am I predicted to fail in the very near future? And what is the accuracy of that prediction? And what decision making do I need to make happen based on that prediction? So analytics. And then lastly, technology, okay? We are believers of a think big, start small approach. It's good to start small and justify the business case with the technology, but then how does the technology scale? Okay, is it just one plant? Do I have 10 plants? You know, what's going on with my architecture, my infrastructure, my IT and OT layer convergence, right? So 4 pillars of a digital strategy, and you'll see me referring back to them during this presentation. So I'm going to start with the business case, right? Business drives everything. Let's look at a smart factory. How do I measure success? Okay. OEE. What's my uptime? What's my performance? What's my quality? What you see here are true numbers. Clients of ours and other clients who have adopted predictive analytics and predictive maintenance type of solutions on their factory floor have been able to dramatically increase their OEE, okay? At minimum, a 5 to 10% gain in OEE, mostly attributed to gains in uptime, utilization of the assets, by being able to predict failures early. And not to mention labor productivity, especially the maintenance labor productivity, because when deploying a predictive maintenance solution, in addition to reducing unplanned downtime and sustaining high levels of uptime, I'm also able to integrate with my spare parts. We have clients and case studies where there are significant reductions in spare parts. You're able to tie predictive insights to your maintenance system, your SAP PM, your CMMS, your enterprise asset management systems, whatever that might be, and you're able to have predictive replenishment of spare parts. You can actually reduce your spare part inventory and you can order new spare parts before the machine actually fails. That's a big ROI in itself, actually. And in addition to that, you're able to start optimizing your maintenance scheduling, okay? You can pinpoint the right place to fix with the right spare part and the right person at the right time, okay? This means you can reduce your mean time to repair. You can fix your machines faster. And we have clients that have even eliminated weekend maintenance completely. It's an overhead activity, and they were able to use predictive analytics like machine health and predictions to be able to come up with a very optimal maintenance schedule and to synchronize that. There's also a case study I'm going to talk about at the end, which is a very strong case study in areas where I call them scrap-rich processes. Scrap-rich, there's a lot of scrap. Casting, injection molding, right? We'll give a case study at the end talking about high-pressure die casting and how an automotive manufacturer was able to use AI and predictive analytics to reduce scrap significantly on the factory floor by using analytics, okay? So what is your why, okay? Are you looking to improve uptime? Are you looking to reduce scrap? Are you looking to improve spare part management? Are you looking to improve your maintenance scheduling, right? Your why dictates technology selection, technology adoption, technology implementation, and scalability, okay? And it helps you drive towards your vision. And your vision is a zero downtime, zero defect operation, okay? So I'm going to talk briefly about 2 case studies, and then I'll go into the technology, okay? Both case studies actually received the AI Leadership Award by the National Association of Manufacturers. Last year, NAM had the first ever AI Leadership Award, as part of their award system. And the Maxion actually received it last year, and Bocar was nominated for it and received it this year. But we see predictive analytics and maintenance 4.0 and quality 4.0 as a four pronged stool, if I may say. Okay, it's a 4-legged seat. The first one is value. Okay, the ability to use predictive maintenance, for example, to detect faults early, improve spare parts, and scale your maintenance activities, to move away from a reactive maintenance approach to a proactive and predictive maintenance approach. That's the vision, okay? But velocity is key, right? Focusing on the right assets and moving in the right direction and rapidly deploying solutions. It's important to understand that these solutions are not new. They've been around, but there are still trial and error approaches that occur, right? And this increases time to deploy, increases time to adoption, and runs into what I call data science projects. I think it's important to always learn from the past and start refraining from PhD and data science projects, okay? So how can you deploy proven AI solutions in 8 to 12 weeks, okay? 8 to 12 weeks, 3 months. And an example of such a velocity was actually done by Maxion Wheel, and I'll show the case study later, okay? And scalability. So now that I've proven it with several templates, several types of machines in my plant, I have 10 manufacturing plants in 3 geographic locations around the world. How do I scale that? Okay. So we talk about creating a center of excellence environment within the customer, right? How can I start training talent within the customer, a center of competence, a COE that could scale it on their own if needed, or supported by an organization like ours or a system integrator type of organization. So scalability is key. And last but not least, actually first and foremost is ROI. Pilot ROIs usually should be within 3 to 6 months, and plant level ROIs must be under 12 months, period, okay? BOCAR, this is very interesting, and I'll show the case study at the end. Predictive quality. So uptime here is not an issue. The issue is scrap. You may be surprised to know that the industry standard level of scrap in high pressure die casting is somewhere between 9 to 12%. Just imagine this for a second. If I'm making 10% scrap on my machine, it's actually considered good. It's industry standard, okay? So I'm making 90% good part and 10% of them get rejected. So that requires improvement, okay? So how can we use analytics, and how can we start correlating the machine data with the part data, that's the quality data, and actually making predictions, right? And even becoming prescriptive and prescribing to the machine and informing the PLC directly, you will make a bad part, change the recipe, offset the recipe, or automatically reject the part. Don't let the part go, right? So there's a robot on the casting cell where we're prescribing data, and the robot picks up the part and automatically segregates it, puts it in a good bin, green, puts it in a red bin, red, okay? And we have to be able to do this within the cycle time of the part. You're making a part every 15 seconds. So the prescriptive analytics and the AI must make decisions within 15 seconds. So we're actually sending data back to the machine within around 6 seconds to beat the cycle time and to allow the robot to act and to make the decision prescriptively on the machine, okay? So again, predictive quality is not something that you would do, big bang, factory-wide. It's important with any type of predictive analytics project to start at the right place, to deploy at the right place, right? On critical assets that are uptime critical assets that are quality or scrap critical, and that would actually deliver the biggest win to the organization, okay? ROI, again, first and foremost, a 1% reduction, just a 1%. We call it the power of 1%. 1% reduction in high pressure die casting, medium-sized plant, is actually minimum $250K per plant per year in annual savings. So out of the 10% industry norm scrap, you only need to reduce 1% to actually achieve almost $250,000 in annual savings. Not to mention, warranty claims, recalls. If my part slips and goes to my next machine and it goes to the customer, you got a big problem. That's priceless, okay? So these are also, ROI things that should be kept into consideration. So this is the output of the analytics. At the end of the day, you have maintenance users and quality users who need to use these tools and to drive ROI for the business, right? And start with the business case. So what's the technology? What can you put today on your factory floor or even in your smart connected products to drive such ROI? Let's talk about it. Let's very quickly look at the history, okay? And it's important to understand that different manufacturers, different companies have different levels of maintenance maturity, okay? Not everybody's built the same. You can actually enter a factory, one factory, and you can find that the stamping department is doing predictive with AI, and the mechanical CNC department is still in a reactive mode. You know, they're waiting for something to fail and they're fixing it. They're firefighting. So my message here is, what's the maintenance maturity of your organization, and what are the right tools to start putting in place in a phased and systematic approach to take us away from firefighting, fail and fix, to preventive, time-based, using digital tools, reliability center maintenance that I know all the SMRP team members know very well from your days of work and certifications and classes and all that good stuff. But moving that into CBM, condition-based maintenance, by starting to collect data, using PLC data, sensor data, and actually becoming a need-based approach to doing maintenance, and to augment that with your existing PM cycles, right? And then going into PHM, which has been named very differently with many types of associations. But I want to define PHM from the first ever conference that I actually attended. Back in 2008, when I first started doing predictive maintenance, one of the first conferences I attended, which is now what, I don't know, almost a long time ago. PHM is a system engineering discipline focusing on detecting, predicting, managing health and status of complex engineered systems. Okay, and I think NASA actually was one of the board members, and they pioneered this. This conference still goes on, by the way, and if you guys have attended the PHM conference, I attended, or I try to attend it at least every year. But this is exactly the vision of a zero downtime operation with which we are working to transition that maturity scale, right? That maturity curve, the maintenance maturity curve, to a PHM type of organization. And there are many solutions out there that do this. Forget the solution. Think about the architecture of this. There's a data lake. I need connectivity. I need to collect the right data with the right type of data quality and data integrity for my analytics, okay? Garbage in, garbage out. Good data in, great analytics out, okay? And then they have to run through templates. We call them templates, okay? Templates are pre-built knowledge hubs, right? You have knowledge of equipment like robots and CNCs and casting and all these things. We've taken that knowledge and we've created solution templates using industrial AI, and I'll show some examples of that. And then you have use cases, right? So looking at it from the left, I have asset data, I have process data, I have potentially worker data, I have quality data. Some of it's coming from the PLC, some of it's coming from sensors that I'm adding to the machine. Some of it's already being collected in my data lake on Azure or Amazon, whatever that might be, or Hadoop clusters that are out there, okay? And they're being crunched somehow by some solution, right? And they're bringing out results. Predictive maintenance. What's my machine health? You know, my maintenance organization doesn't really care if I'm using logistic regression to compare my vibration signals. They care about what's in it for me so I can improve maintenance in my plant today and generate ROI. So they care about reliable measures of what's my machine health, what's my prediction of an RUL, remaining useful life, when will this machine or component in the machine fail, and what is the degree of accuracy so I can trust in the data, so I can make decisions about scheduling and decisions about spare parts. And what's my diagnostics? Do I need to fix the whole robot, or my robot has 6 axes, it's a complex piece of equipment, there's a lot of moving parts. Do I just fix joint number 5 or joint number 6, right? And is it my temperature signal, or is it my motor current on my axis causing a backlash, okay? So that's the type of predictive maintenance insights that need to be delivered to the maintenance organization and presented to them intuitively so they can use it to take action. And on the other side, the quality organization, predictive quality. So here I'm not focusing on the asset, I'm focusing on the part I'm producing. What's my part health? Am I going to make a good part, or am I going to make a bad part or a suspect part? So I can prescribe and make decisions whether I manually remove that part from the machine, or I feed data to the machine and automatically prescribe an action, right? This is a systematic process that is not new. It's been around for a long time, maybe 20 plus years. It's been used for many years, but the question is always the devil's in the details, right? How can I take this systematic process and apply it to a variety of solution templates and heterogeneous type of manufacturing and non-manufacturing processes out there, right? Data is key. Data quality, data integrity, collected in the right way, sustainable and affordable, okay? Not everybody's blessed with brand new machines with brand new PLCs where I can plug and play, right? There's a lot of antiquated legacy machines out there, and they may need sensorization. So what is that recipe? What's affordable sensors and hardware that can be used to capture the right data from the assets? Then what do I do with the data? There's a series of machine learning algorithms that are part of the artificial intelligence domain of science, right? What is the right algorithm to use to process the data, signal processing, removing outliers and denoising and just cleansing the data so that it's usable for the statistics side of the solution. So feature extraction, what are the indicators, the metrics? Can I reduce the dimension of a 20 kilohertz sampled vibration signal? 20 kilohertz is 20,000 samples per second, okay? Do I need to work with 20,000 samples per second? No. I need to extract features, statistical indicators, reduce the dimension of the data, and then use the data to train an AI ML model that learns the health of the machine, okay? Builds a fingerprint, a signature, and starts to trend that over time, okay? And starts to offer predictions with an accuracy, all right? And starts to do diagnosis. And diagnosis could become quite intricate, actually. If you're looking at a bearing, I mean, the bearing specs are known and the bearing harmonics are known. And you can start to fuse some physics-based model with, you know, data-driven models and come up with a hybrid model and be able to actually tell the maintenance organization, your bearing is going to fail because the outer race is going to go bad or the inner race is going to go bad, right? So these 6 steps, which are proven in the literature, they've been studied for many, many processes out there. How can we take them to market and deploy them very quickly, affordably, within 8 to 12 week deployment cycles, okay? So that maintenance and quality folks can start to use them immediately on the factory floor. Templates. 25 plus solution templates. Robots, CNC machines, advanced processes like casting and molding, stamping equipment, whether you have hydraulic stampers or whether you have large automotive Schuler stamping machines or just your old mechanical presses or hydraulic presses, right? And not to forget the ancillary components that are surrounding the factory or connected to the assembly lines. Your pumps, your compressors, your chillers, your motors, your gearboxes, right? So knowing the variety, right, the breadth and depth of the type of manufacturing processes out there today, how can we apply that 6-step process so that we can very quickly take data from a robot or a CNC or a stamping machine? And those are the 2 cases I want to show you guys today briefly, and be able to do 4 things. Number 1, apply that 6-step process, train the models, validate the models, and go live quickly and provide trusted data and insights to the manufacturing department. Second, have a clear understanding of connectivity needs. What's my data map? Okay. What parameters at minimum do I need from the PLC, from the CNC, or from sensors that I might need to add to the machine? Connectivity. Second, data collection. How do I capture that data and make it available through a historian, through a SCADA system, or directly to a IoT type of solution? And third, what is that analytics workflow look like? What are the machine learning algorithms needed? How are they trained and validated? Okay. This allows for quick deployment. This allows for scalable solutions where you can train your actual department, your manufacturing department, to actually take them, build a center of competence around it, and scale it yourself around the manufacturing floor. And last but not least, keep the ROI in mind, right? Some of these templates can be retooled for predictive maintenance purposes, and some of them can be retooled for predictive quality purposes, okay? Again, depending on the application. I'm gonna show 3 case studies today briefly. I'm going to talk about robots, predictive maintenance. I'm going to talk about CNC machine predictive maintenance, and I'll conclude with a predictive quality case on casting. Okay. Very quickly, how do you implement these things? I will not spend time here. Depends on your architecture, but it's just very important to understand that there is usually two sources of data. You have machine data coming from the control. There's different protocols, languages that those solutions should work with. And then you have add-on sensors like vibration that may be required depending on the template. In the case of robotics, for example, I'm going to share with you how you can actually do it without any sensors, sensor-less, non-intrusive, okay, directly from the robot PLC, save costs on the hardware. But on the CNC machines, looking at a spindle bearing, a vibration sensor, for example, is required to be part of that template. And then once that data is digested and aggregated, and in some cases, edge analytics is applied on the data because the bandwidth and the data collection frequency and all that, the metadata or the features or the health are sent to an application. And this application could be an on-premise application or a cloud-based application. And this is your user experience. Your maintenance organization need to log in and be able to intuitively use these systems to make decisions, okay? So it's important to understand these layers within your organization. And I tell you, one of the biggest challenge is really connectivity, okay? It's the infrastructure, it's the networking, it's the cabling, it's the legacy machines and how to add sensors on those legacy machines to get the data you want, okay? Regardless of the size of the company, small or large, infrastructure and connectivity is always a hindrance, and it's something that we must take into consideration when we do our OT strategy, right? And to assess the maintenance maturity around that. So let's talk about case studies very briefly, okay? And I want to start with robots. Predictive maintenance. Let's talk about predictive maintenance for industrial robots. I want to share with you first, right here, before the animation goes. You know, predictive maintenance is not a solution for all problems, okay? You cannot expect to deploy a predictive maintenance solution on a robot and be able to catch everything. That is a myth. It's important to still do your PMs. There are specific PMs that can never be caught by a predictive maintenance solution. I got a cable failing. I got a dead battery in my controller. I got some lubrication issues, you know. Sorry, predictive maintenance will not catch this for you. Predictive maintenance usually catches high impact issues, okay? I got a gear backlash on my joints, on my axis. I got a bearing failure. I got a mechanical motor brake type of failure, right? These are addressed by predictive maintenance. And in the case of industrial robots, especially ones where uptime is critical, in the automotive industry, for example, 1 minute of downtime on a robot could be near $10,000 to $20,000 per minute. Those are real numbers because basically your line is off and you're not making cars, right? It's important to have solutions that address any robot OEM. So I have KUKA, I have Denso, I have Fanuc, right? How can we build those solutions to be interoperable with a variety of OEMs and a variety of control types, right? It's key. The data map, how can I capture key parameters like torque and speed and position directly from the PLC? That's my connectivity. And ensuring that data flows into my AI ML algorithms and allowing me to drive intuitive feedback to the maintenance organization, health, prediction, diagnosis, right? So when my maintenance team goes in, you know, keeping in mind that the maintenance organization is by no means a PhD or a data scientist, they are skilled at fixing machines. Solutions need to be built in that manner. The user experience, the UI must be intuitive for the end users. And therefore, as a maintenance person, I want to know health. Is my machine healthy or is it deviating from my baseline, right? I want to know predictions. What is a prediction with an accuracy? And I want to receive a predictive alert by text or by email, or I want you to create in my maintenance system an automatic alert so I can be informed with a work order. And I want to know diagnostics. Do I need to go in and fix all the 6 bearings on all the 6 joints of the robot? The answer is no. By doing predictive maintenance and assessing every joint of the robot, we're actually able to pinpoint the specific joint or axis that should be fixed, okay? And that's exactly what solutions like this will make happen, okay? So regardless of the solution you select, make sure that the user experience of the solution meets the needs of the maintenance organization and other, key users that will be using the solution, okay? ROI. This is just an example from an automotive OEM. Those are actually real numbers. 500 robots, but let's face the facts, only 30 robots fail every year. I mean, robots are strong equipment, okay? They're not supposed to fail. But when those 30 fail out of 500, 1 minute of failure is $10,000. And that's actually a low number. 30 minutes is usually a severe downtime because you need to fix the robot. You're, fighting fires. That's a cost of a single robot failure. If we deploy a predictive maintenance solution that only catches half of that, that's 15 out of 30, okay? Huge ROI, significant ROI for the business. And I know you're looking at this, oh, the numbers are so big, my operation is not so big. Just plug in your numbers, plug in your number of assets. We have an ROI calculator I can share with you, very simple. Plug in your 1 minute of downtime or 1 minute quality costs that you have, right? Not to mention spare parts, not to mention maintenance labor time, right? This is strictly the power of uptime and an example in an uptime critical type of industry. Machine tools. Very different from robotics. Much more complex, actually. A lot more moving parts. So, one template is not going to help you solve all your problems with machine tools. You need a series of templates. We need to understand that there's a lot of moving parts, but I cannot fix everything. It's an 80-20 rule, right? If I fix 20% of issues, I can capture 80% of my ROI. So I got a spindle bearing with tools, right? And my tools can unbalance if my bearing has a problem, and my spindle bearing itself degrades, right? Feed axis, that's your ball screw, that's your linear guideway on the CNC machine. You have your gib, you even have your coolant system. A lot of folks are having issues with contaminated coolants, or they don't fix the coolant in time, and it leads to making bad parts on the machine. So a series of predictive analytics templates and understanding of the domain here is required, okay? And the data map is different actually from component to component, because in the case of a spindle bearing, I need an add-on sensor like vibration. In the case of the feed axis or the linear ball screw of the machine, we have come to find that you actually don't need any sensors. There are specific parameters from the CNC control, like the position of the axis, the actual position, the commanded position, the current, the temperature. It's a known data map that can be used as an input to the ML or AI model that can provide you very high accuracy predictions of the feed axis or ball screw, preload loss issues, they call it preload loss, or lubrication starvation issues, right? So again, specific failure modes. And this is again an example. That's your data map. I need vibration and the motor current and the spindle speed on my spindle, for example. Okay, so that's an add-on sensor. How do I get the data? The vibration comes from an add-on sensor. The red items are coming from a machine protocol, which is called MT Connect, but you can also receive it using OPC UA or many other protocols that are usually natively available on the machines. And user experience, my health, my prediction. And please notice, unlike a robot, this is not linear degradation. It's a non-linear degradation trend for a bearing. And that's, again, part of the analytics workflow, and the machine learning algorithm that is used for prediction. It's different than the machine learning algorithm used in the robotics template. Diagnosis. So I know the bearing, I know the specs, I know the harmonics, and based on the tracking, I'm actually diagnosing that you're going to have an 8 kilohertz band frequency of failure on this bearing, okay? We can also diagnose outer race, inner race, ballpark frequency type of failures, right? If the bearing geometries are known, as an example. So from data to features to health to predictions, right? An analytics workflow requiring data and connectivity to the asset. Final example, casting. Casting is a whole different animal, okay? There's a lot of moving parts. So I just went from a small, medium, large in terms of complexity, okay? Robots, CNC machines, casting, just to show you the variety of this. A high pressure die casting type of asset has over 80 to 100 process parameters that are collected for every shot of injected aluminum or zinc or whatever you're doing on the casting machine, right? In this case, it's an aluminum high pressure die casting machine. And for every shot, which happens every few seconds, okay, or 10 to 15 seconds, you get about 100 data parameters. And the key data parameters are kind of outlined on the right here: your pressures, your airflows, your temperatures, and oil type of data. And at the same time, there are thresholds for these parameters, right? So there has to be a way to start correlating those parameters to the actual quality of my part, okay? Am I running those parameters as a multivariate analysis with the thresholds and everything to meet the specs and to make a good part, or is it a suspect part, or is it a bad part? Green, yellow, red, right? And if it's yellow or red, it's automatically prescribed or automatically rejected by the machine before it slips to the next machine. So what you're seeing here is just an example, okay? And I wanted to quickly mention the points below. So for each shot or die open event, data is collected, and it's truly big data. It's 100 parameters every few seconds, okay? Within 6 seconds, the solution needs to make a decision whether this is a good or a bad part. So you need more training data here. You also need prescriptive capability to be able to feed data back to the machine and to command the machine to take an action, okay? And the solution needs to what we call auto part segregation, okay? Automatically segregate the part, good or bad. So this approach of predictive quality or quality 4.0 is mission critical. It's always running, it's always live, it's always predicting, it's always prescribing within seconds. It's mission critical to the operation. So deploying a predictive quality solution in terms of architecture is also different than a predictive maintenance solution, because predictive maintenance in some way is less mission critical. I mean, the machine is not going to suddenly fail in the next hour. There's a trend to it. But in predictive quality, I need to be very decisive, and I need to be collecting data at a high frequency and making decisions at a high frequency. So again, architecture and infrastructure assessment here is different and must be considered, right? So let me give a summary of this journey that we just went through, okay? And at the end of the day, it's about winning. It's about winning ROI with advanced technology. AI, machine learning, predictive analytics is advanced technology, requiring folks like data scientists and talents who are able to configure and work with those solutions, but at the same time, present those solutions intuitively to maintenance and quality who are non-PhDs and non-data scientists who are expect to work with them, right? So it's about ROI. And therefore, I like to start with the slide in conclusion. This 3 slides to go, and this is my first one. Don't start here. Don't start with technology and data management. Just please don't do that. Start here. What's my process? What's my team? Do I have the folks that can make this happen? Change management. Start here. Do a maturity assessment. Do a maturity assessment. Do I have the right teams? Do I have the right roles? Do I have the right skill sets? How can I make this happen? What's my center of competence? What's my center of excellence? What's my business case? Who are my key stakeholders? Build the foundation for success. There's always a 3-legged stool: technology, process, and people. And your weakest link will make you fail or succeed, okay? And if the weakest link is people, and unfortunately it usually is, it's important for me to focus there first and empower them and deploy the technology and the data management to support them. It's a multidisciplinary approach. My second piece of advice is very simple statement, but I'll show a bigger version of it. Think big. It's good to have a strategy, zero downtime, zero defect operation all the way, but start small. Select the right plant, select the right area of the plant, select the right combination of technology, process, people, and prove the value Prove the value quickly within 8 to 12 weeks. Don't prove the value within 6 to 12 months. And scale fast. Have your organization trained or work with the right integrators to allow that scalability using templates and other approaches. And if you want to look at the bigger version of this, we call it a discover, design, deliver process. Do your assessment. It's important. Understand your maturity, understand the technology, people, process, driving behavior. Do the right workshops at the right place with the right people. Your workshops should deliver a very clear gap analysis. Where are you from reality, okay? Where are you benchmarked versus others that are in the same journey? And then understand your hardware, software, services clearly from your vendors. No hidden fees, no change requests. Everything should be clear. And this leads to your proof of value. You have now laid the foundation that allows you to do two things. Technical deployment, business case. Technology plus business case is a proof of value. Please notice I didn't say POC. These are not concepts, guys. Sorry. These are things that are proven and being used in the industry today. And if you couple the right technology with the right business case, you will prove value. And once you prove the value, scale it. What went well? What can I improve? What's my lessons learned? My templates for success. Build your library of templates for your organization and train your center of excellence and build a partner ecosystem. The right integrator, the right technology vendors, academic institutions if required, and use that to scale across your operation. So in conclusion, I thank you for your time. I want to take questions in the next 15 minutes, and I will leave you with those simple thoughts. Think big, start small, act now. Make it operational today with a proof of value. Please don't wait. Whether you have a smart connected factory, which was my whole case studies I showed you today, go ahead with the vision, but also keep in mind if you're making products, I mean, the same analytics, the same thought flow could also support you to offer new business models and revenue generation models to improve your end user and your customer satisfaction, okay? And consider your weakest link, consider assessments and understanding your maturity and deploying these solutions in the right way with a phase approach. And this is my info. Please connect with me. Back to you, Sean.
Great, thank you. Got a few questions for you here. You made reference to this concept being used to improve spares. Would greatly appreciate if you could shed more light on this.
Absolutely. It always depends how the spare parts are maintained. Usually they're maintained in a CMMS system like an EAM, SAP, Infor, IBM Maximo, whatever that might be, or at least a database. So we believe there is an approach to correlate the predictive RUL, the remaining useful lives from these algorithms to your actual spare parts system. So you could reduce, ideally, your number of spare parts waiting for things to fail. And by having predictive insights, you can tie it to actually schedule the order of spare parts from your vendor or whatever to arrive in time to fix the asset. And I give you a short example: bearings on a robot, or actually another example, an aerospace client with spindle bearings. Each spindle bearing on a CNC machine cost them 50 grand. Imagine that, 50K, and they have to keep. They have like 100 machines in the shop. So you're telling me I got to keep 50 spindle bearings at 50 grand each, waiting for my spindle bearing to fail? The answer is no. If I'm using predictive analytics on my spindle bearing, I could reduce the number of spindle bearing overhead, and I could actually just in time integrate and order the spindle bearing before failure. So there's a lot of these case studies. Reach out to me and I'm happy to actually send you a few.
All right. Next question. Effective predictive maintenance will have as a consequence a reduction in RUL, remaining useful life, i.e. don't leave too much tread on the tires when you change them. What tools, techniques have you seen for calculating RUL on parts that have been replaced? Calculating RUL for mechanical parts will be different than for electrical components.
Yeah, most of our experience actually stems from mechanical parts, like bearings and the other examples that I showed today. I mean, there's multiple RUL type of algorithms out there that we've utilized. Some of them are regression based. Some of them are Markovian based, stochastic based. I mean, there's quite a few. Again, it depends, as in the robot case, if it's a linear degradation type of prediction, or if it's a non-linear prediction trend, like in the bearing case I showed. So again, it depends on the process, the solution template, the understanding of the data, and also the availability of historical data. And I didn't touch on this too much. Whether we're doing unsupervised learning where I have no history, or supervised learning where I have history, right? It's always nice to have, run to failure data for some of these assets, but I know it's not easy to have. So the supervised versus unsupervised aspect of it also kind of dictates the type of prediction algorithm that I might be selecting. Yeah. I hope that sheds some light on your question.
All right. Next question. Would you please speak a bit more about the data training phase of machine learning? What do you actually do to teach the eventual algorithms or pattern recognition models?
Yeah, there is a need to have the right amount of data to train these models, which go into those template examples I've shown. For some of the templates, we usually require about 2 to 4 weeks worth of data. Okay, that obviously has data quality and integrity to it. There are some check marks there we have to go through about the sampling rate and the sampling frequency and all these things. But usually a 2 to 4 week window of baseline data allows us to train the model. And again, if it's unsupervised, we then run the model and we look at just deviation from the baseline. But if it is supervised, we would need 2 to 4 weeks for each category of data, right? Labeled data, good behavior, and then fault condition 1, 2, 3, 4, 5, right? So again, our recommendation to have statistical accuracy to what we're doing in the baselining of the AI, which is the training of the AI, is 2 to 4 weeks of baseline data.
All right. Next question. Any success in open loop systems?
Great question. And a short answer, I do not know what are open loop systems. So maybe I know it by a different term. Please email me. Sorry, answer is no.
All right. Next question. How accurate is the computation of RUL compared to maintenance history?
That question really brings a critical point that I also did not mention. Thank you for bringing that up. It is important to have initially correlated data, if possible, between the maintenance events that happened, usually through the CMMS or EAM system, with the actual training data, right? Where I'm training my models or creating my baseline. So we always see that the predictive solutions, yes, you can deploy them standalone, but it's important to validate them by integrations with the maintenance system. Usually in a phase 2, the integration would occur, okay? So you make an excellent point. Usually when we're looking at the initial data sets, we're always asking for maintenance records to correlate with the data timestamp, or at least expert feedback from the maintenance organization on, what events do you see, what failure modes do you see? So that assessment type of conversation is critical, and the correlation between the data and the maintenance record is actually key. But it is a challenge because at many times the maintenance data is not there, or it's in bad shape, or it's just not correlated, right? So these are challenges that we have to go through.
All right. And a couple that were sent to me directly. What challenges have you faced in your organization while implementing predictive analytics?
A few challenges that I'd like to summarize from my presentation, I would say, on the OT side, right, the operation side, the connectivity and the infrastructure are really a hindrance. The legacy machines on the factory floor that may require sensorization, right, which is a cost. The overall infrastructure, the ability to do work on premise versus on the edge versus on the cloud, right? So these OT type of conversations and the age of machines and challenges on the networking sometimes is an issue, especially when you start going into aerospace, defense, and heavily regulated industries. It becomes very time consuming. And I would say the other challenge is really, again, on the people, the change management side. I mean, imagine you're a maintenance person and you have a validated, great intuitive solution in front of you that's telling you, you need to go fix joint 5 on the robot, it's going to fail in the next 2 weeks, right? So the people side, are you going to trust in me telling you this and you're going to actually go and fix it prior to failure? Or what's the human element of the whole decision-making process here? So, training and really empowering the workers to understand the technology they're using will ensure success of these types of projects.
All right, next question. What are the challenges of working with older equipment?
Just add-on sensors. I mean, if I take the Maxion example that I just showed you guys earlier, which received the AI award last year, one of the reasons it received the AI award is those machines make steel wheels, and they are from the 1950s. I swear to you, there's a brass tag on the machine that says 1950, okay? The machines are running. They're making wheels. The wheels are going on trucks and probably your car, okay? But the situation is there is no PLC on the machine. It's relay logic, okay? How can I put meaningful sensors on a very antiquated machine? And so we have to sensorize, right? So we could have put sensors that are worth $100,000, but we decided to put sensors that are worth $10,000 because we believe that there is the right data with the right sensors, very affordable to deliver the business case, which is predictive maintenance on the machine, right? So we don't believe in over sensorization and over engineering, especially with legacy machines. But I would say cost of hardware, sensorization, how you're going to mount the sensors, how you're going to maintain the sensors, this whole data collection strategy for legacy machines is critical for the cost benefit analysis of the project.
Right. Next question. Do you think AI machine learning should trigger an update of the old-fashioned but still widely used failure pattern percentage from RCM?
No, period. Next question. That was a joke. The first ever time that I worked in a maintenance field, I worked as an intern at IBM right out of college, University of Arizona. And that was more than 20 years ago. And I was an RCA engineer. I was actually looking at reliability centered analysis of very big hard drives that IBM used to make. And we were damn good at it. And we did the Weibull distribution and the bathtub curve and all these great things, I think there's a link. I think there's a transition. There is the reactive RCM approach, and there are elements of it that should be studied, especially when it comes to run to failure data, right? And the distribution of when an actual part is built based on the specs to fail. And I believe there are hybrid models that would take such physics-based and data-driven approaches and provide even more accurate insights. But again, I'm not an expert in that area. We've been very focused on data-driven analytics, and we've actually not ventured too much onto the RCA side, but it brings back memories. So thank you for the question.
All right. Is the machine learning sequence conducted at each machine component replacement, thinking in terms of repair efficiency, variance of component quality, etc.?
Say that one more time, Sean.
Is the machine learning sequence conducted at each machine component replacement, thinking in terms of repair efficiency, variance of component quality, etc.?
That's a good question, actually. So there is a need, obviously, to retrain those models, right? So when you fix the robot joint, I mean, there has to be a way either to manually re-baseline and retrain the model, or we have started to adopt ways to automate the re-baselining. So to catch that a repair was made somehow, maybe through the maintenance system or a link somehow, and then automatically retune the model parameters and then rerun it. And then we might find that the baseline is the same than before, or it might be lower, or it might be higher. And in some cases, actually, the difference in baselines indicates something. It indicates maybe the maintenance person didn't fix it right, or maybe the spare part that was used was not the right spare part. I mean, there are hints, or maybe just something happened different on the machine, so the baseline changed, right? So I appreciate what you're saying. It's important to be able to link it to the repair and have an approach to manually or automatically re-baseline, and also compare the new baseline with the old baseline and make sure there is an impact on the repair or the spare part or the machine, right? There are some hints that you can see in the data there. It's an excellent question. Yeah.
All right. Well, we are about out of time. So to wrap up, I'd like to just once again thank Mo, our speaker. That was a great presentation. Like to thank our attendees for joining us today, of course. And also like to encourage you, if you'd like to continue the conversation, please feel free to reach out to Mo. The website does offer you the opportunity to private message him. His email address is in his profile also, and you do also have the opportunity to set up private meetings. Last reminder is just once again to fill out that survey. You'll find the survey link underneath the description of this session. And with that, I will thank everybody one more time and encourage you to please join us for our closing panel session at 3:30.
Thank you for the opportunity, Sean. Maybe see you in Denver in June, okay?
I'm hoping so. Take care, everybody.
Stay
Thank you.
healthy.